This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
Good evening and welcome to the Jeffrey B. Graham Perspectives on Ocean Science Lecture Series. My name is Harry Helling. I'm the Executive Director of the Birch Aquarium at Scripps Institution of Oceanography. It is my great pleasure to introduce our speakers for this evening, Sarah Giddings and Julie Thomas. Sarah Giddings is a coastal physical oceanographer specializing in estuarine and coastal processes with an interest in how physics impacts important biological and chemical processes in the coastal environment. She uses a variety of scientific approaches ranging from field experiments that directly measure water properties and movements to numerical models that simulate flow in coastal waters. She started as an assistant professor at Scripps Institution of Oceanography in January 2014 and is currently involved in research projects around the world, including several right here in local Southern California waters. Julie Thomas has worked for over 39 years at Scripps Institution of Oceanography in La Jolla, California, and she serves as the program manager for CDIP. Some of you may have heard that. That stands for the Coastal Data Information Program. She's also the executive director of another prominent program called SCOOS, or Southern California Coastal Ocean Observing System. Her priority is to maintain standards for collecting and disseminating high-quality data throughout the maritime community and to advocate for integration and communication of information that helps ensure safety, economic and environmental resilience, and sustainable use of our coastal ocean. We are very fortunate to have both of them here tonight for their talk titled El Nino and Our Urban Oceans.
Thank you very much, Harry. Good evening and welcome. Some of you might have been here in time to see the video that we took last week when we did have large waves and they were hitting our Jolla Shores, and it was pretty impressive on some of the homes there. But I thought I would also include this, start out with this picture from 1983 of the Marine Room. And some of you might have remembered that. The windows actually smashed in, and now you can go there for high tide dinner. I think they have an advertisement for that. But it's very similar. We had the same type of waves. Interestingly enough, we've actually had fairly large waves these last couple storms, and they've had a lot of impact on our coastal zone. So tonight we're going to talk about a little bit about El Nino now. What does it mean to us? I just have a couple slides on that. And then we're going to talk about the value of some of the sustained programs. Harry mentioned CDIP and SCOOS. Those are two programs I'm involved with. We have very local observations. We feel these are critical for really providing baseline information for our climate changes and signals such as El Nino. And we're also going to talk about the coastal impacts. What does that actually mean to our coastal zone? Look a little bit into the future and talk we have a slide or two on the Citizen Science Project where you can become involved also. So where are we right now? Where was all the rain that we were expecting of? Godzilla, El Nino, we were all excited, lots and lots of rain. But it's complex to measure these El Nino impacts on our coastline. You know, we have to have those warm temperatures starting at the equator. They move, the water moves over. We have those temperatures moving along the west coast of the U.S. But then we also have to have the jet stream. It usually follows where in the red up there we have the jet stream lowering, this one red right here coming down. But what happened particularly in February, we had a high pressure system. It kept pushing the jet stream further north. So we didn't really get as much rain as we were hoping for during this El Nino season. What's happening right now, the El Nino temperatures are weakening at the equator, and there's particularly in the subsurface, there's upwellings. It's bringing up some of the cooler waters, so it is cooling down. But let's take what we can get. We've had up until March, through March of last week, a few days ago, we ended up having over 6 inches of rain. During that time, for our other 2 strong El Niños, 1982 to 83, we had 9 inches, and the 97, 98, 12 inches. So this just gives you a comparison. I'm sure you've heard that not all El Niños bring high amounts of precipitation. Often the stronger ones do, but it is about a 50-50 chance whether or not you will get a lot of precipitation with these El Niños. But we've had some impacts. We've had some deep sinkholes, and other pavement and roads have been infected by the rains. We still have a chance for the rest of March, April, and May, and we'll see what we get as far as any additional precipitation. We'll take it. Okay, so I'm going to jump right into these observational programs. On the left, you see a picture of the west coast of the U.S. These are the wave buoys that are deployed by the CDIP program, Coastal Data Information Program. This program is mainly sponsored by the Army Corps of Engineers, the California Department of Boating and Waterways in California. You can see the propensity of wave buoys within California. That's because we actually have state funding that comes into sponsoring this program. The U.S. Navy around San Nicolas Island, some of our islands offshore, those buoys are sponsored by the U.S. Navy, and then we have industry partners also. On the right-hand side is the SCOOS program, Southern California Coastal Ocean Observing Program. This is much broader than the measurement of waves and temperature. It includes a lot of water quality. We're doing harmful algal blooms. I wanted to mention that all of the observations that I'm going to be showing tonight are available online. These are real-time programs, CDIP at ucsd.edu and scoos.org. Also, one more thing about the CDIP program is that it is nationwide. So what you see here are the West Coast buoys, but it is the same buoys that we have in the Caribbean, the East Coast, and the Pacific region. And when you listen to Scott Bass on NPR in the morning and he talks about the surf report, that's what's, these are the buoys that are transmitting that data. The data goes right from the buoy itself, so like 5 miles off of Mission Bay, we have one. It transmits to the Iridium satellite, over to the Department of Defense gateway in Honolulu, back to Scripps for quality control, and out to the National Data Buoy Center, who then transmits it to the National Weather Service, and that takes 2 to 4 minutes. So it updates every half hour. These data are online, and you can monitor these waves yourself. Okay, so first of all, I'm going to talk about sea surface temperature monitoring within Southern California. So these shore stations are sponsored by SCOOS. We have one at Scripps Pier, Newport, Santa Monica, and Stearns Wharf Pier up near Santa Barbara. And this is on the left here is what it looks like underwater. There's a conduit off of Scripps Pier, goes down about 5 meters, and it takes hourly sampling. You can see we were hitting 77 degrees Fahrenheit on that shore station. Actually, that was the sea surface temperature. Part of it was around 77. And once again, this collaborates with the warm water that we've been seeing. So now I'm going to kind of step through these collaborations of what was predicted with the El Nino warm waters. The impacts are several. I'm sure you've heard on the news that we've had species show up that are not local to here. One of them is this Pacific seahorse was found in San Diego Bay, and then of course the tuna crabs that are dead on the beach in Ocean Beach. That was in June 2015. Now this is the manual shore station. What I actually just talked about was the automated shore station, because there's no human intervention there to collect that data. This manual one, we have over 100-year record of someone physically walking out to the end of the pier at Scripps and taking a water sample. And they analyze it, and we have sea surface temperatures. So this started back in 1916. We're one of a couple places in the world, I think, that have this long a record. Funded by the Department of Boating and Waterways, by the way, for the most part. Another program, this is, has some funding through SCOOS and other parts of NOAA, are these gliders that Dan Rudnick, a researcher here at Scripps, runs this program. For those of you that aren't familiar with the gliders, we have two transects out here off of Dana Point and off of Point Conception. These little things right here, you can bring up in real time and actually see where the glider is. So as the glider is moving along that transect, you can see what part of the transect it's on. It dives down, it's a self-propelled underwater instrument. It dives down to about 3,000 feet. That's the capability. I think it's a little bit shallower off of our coast, off of Dana Point. And it takes about 6 hours for it to make a complete dive and surface, and it covers about 3.7 miles during that time period. And we go about 124 miles offshore. What is so incredible about these is that we get all of this profile data. So not only from the surface, but all the way to the bottom of the ocean, we get the complete temperature, salinity, aragonite, all these parameters that Dan is collecting. These are all available online. Another program that's had quite a history here at Scripps, I'm sure many of you are familiar with Cal Coffee, the Cooperative California Fisheries program. And once again, they are measuring profile data on the ship transects. One of the glider transects actually overlaps with the Cal Coffee transect, so we're getting a really comprehensive picture of what's happening along these areas, along this region. And this is just one of the profiles from July 2014 and then November 2015. You can see the dark red would be the warmest areas, and you can see how they're moving around. These, by the way, are difference maps. So we found about 5.4 degrees Fahrenheit warmer during this El Nino season. And I wanted to bring in that the wave buoys through the CDIP program also have a thermistor right at the bottom of the buoy, and it will measure sea surface temperature. And this is a plot, so it's from 1997 to 2014, and the gray in the background is actually an average of all of the years. The important one to look is this magenta. Look at how high it is there. Once again, 77 degrees. This is Mission Bay offshore. It's about 5 miles west of Mission Bay Channel. And then right here, 2016, we're still up there. We're still having this red. It is very warm waters. So we're really seeing a lot of impacts from these warm water conditions. One of them is our kelp is suffering. Our kelp is, we have an invasive species called Sargassum bloom, or devil's weed, and it's found down here. And as the kelp is stressed with the warmer water, it doesn't have the survivability against this invasive species. Dr. Ed Parnell is one of the research scientists here, and you can read his quote, but really he feels that this warm water from the El Nino will eventually eradicate the kelp, and is concerned about it very much. So we'll see. We're tracking it. Once again, these observations are really critical because we can track these ecosystems' impacts. This is a picture of one of the wave buoys that would be 5 miles west of Mission Bay. There's also one 10 miles west of Point Loma, and about 3 miles west of Torrey Pines, about 5 miles west of Oceanside. We're very fortunate to have this whole suite of wave buoys here. And I wanted to bring up some of these high waves that we have seen during the last couple months, because some of our biggest waves that we've actually measured in this area have been from the past few storms. So you can see that in February 1st, we did have quite a storm come through with wave action. We were measuring 32-foot waves, 12-foot at the end of the pier here. That's only in 20 to 25 feet of water there. So 12-foot waves were breaking on the pier, and then off of Mission Bay, 29-foot waves. So that's pretty significant wave action at this time. This photo in the upper right was part of the video that you just saw, so it was taken last week with waves breaking on the homes at Jolla Shores. Hopefully there's no one in the audience that lives there and has any damage to anything. You can see from our Torrey Pines buoy that we were measuring 20-foot waves on February 1st, and the blue on there is Torrey Pines, red is Mission Bay, green is Point Loma. All of our buoys were really getting high waves during that time. And then this plot is kind of busy, but the take-home message here, the gray is the average in the background from 2001 to 2016 of our wave buoys, and the red is during 2015. So we had quite a few substantial storms in 2015, but going into 2016, that's where we really had these high waves here. So we've had quite a bit of impact. Okay, so now I'm going to come even closer to the shore, along the beach. And what do we have to measure our sand elevations? This is really critical because I'm sure as local residents you know that during the summertime we have wider beaches, then the storms come, and then our beaches are narrower during the winter. But it's good to measure those because we need to quantify this. It will help for any sea level rise projections that we do for the future. It will help the local communities, and I think Sarah's going to talk a little bit more about this. But I wanted to just show you some of the measuring tools. This is Bob Goose's work here at Scripps, research scientist. This is actually Bob right here pulling a dolly along. These have GPS on them. They're measuring elevation. He's out in the water here. We have an ATV with the GPS disc right here. We have the jet ski that does sonic depth finding. So we do run the jet skis offshore, and we get that whole profile through the surf zone. That's a very difficult profile to get. Usually you can get bathymetric surveys further offshore outside the surf zone, or we can get the beach component, but getting that surf zone area is difficult. So what have we seen with our beaches? This is a picture of Cardiff. And this was taken on March 6th, so last week, and the beach is very narrow here. If any of you walk that beach, you know that it's actually cobbles right now. So we started this El Nino winter with a really wide beach. Anything above this black line, the zero line, is a wide beach. That's what's building up. That's the sand building up on the beach. And one reason why we have been fortunate this winter and we haven't seen too much coastal damage, even though we've had these big waves, is because we've had this buffer zone. We've had this really wide beach that we started out with. But now look at it. It's been eroding. Every storm comes through and it erodes and it erodes. So we end up with this really narrow beach now and cobbles on our beach. So we'll see if we have any larger storms this winter that have large waves, there could be more impact to our shoreline. Okay, so now we have that information about the beach, but really what we want to do is work with the homeowners, this is Cardiff State Park, with the restaurants that are there, the Chart House, Pacific Grill. We want to work with the state parks campgrounds, with the city planners that have to go out and put the cones at night if the waves are actually overtopping on the coast highway. So we've started a catalog where we're actually cataloging all the events, the historical events where there was flooding along our coastline. We're only doing this for a couple regions. We're starting out with Cardiff because we have very, very good high resolution measurements there, but some of the other areas that we're cataloging also. And you're not going to be able to read this table, but we have the observation date, the location, we have who observed the flooding, and what the wave height was, the period of the wave during that flood event, and we're actually getting some pictures, photos of that flooding event, so that eventually a homeowner or a restaurant owner can go back and say, oh yeah, and March 2016, we had 12-foot waves, and this is how far it came up onto our shoreline and or onto our sidewalk or whatever it might be. And this is what we call our 3-day flood index. The dark blue is the tide, so these are our high tides, and the light blue would be the waves. So we have instances that we know now if it is high tide and some of those large wave events that I showed you previously, when the combination exceeds the yellow line, this is what happens. We get flooding into Seaside parking lot at Cardiff. That's the South Cardiff parking lot. If it actually exceeds this moderate flooding threshold that we've determined, then we know that 101 will actually overtop and there will be spray up on the shoreline. And that's actually my commute in the morning, and believe it or not, I've had pebbles end up on my windshield over the past several years as I drive to work, because the spray has actually come right up onto the highway. So these are important. All of these observations are very important to sustain. They give us a great baseline infrastructure to tell us what is going on right now. It also tells us about a climate signal. It gives us the history to track climate signals. And it also helps to validate our nowcast and forecast models, because we definitely don't want to be surprised, like this lady up in Ventura who opened her door to her living room and voila, there were the waves. So that's kind of my pitch for why we need to have these real-time observations. We want to inform the public more, and we want to engage you more. And now Sarah will continue. Thank you.
Thanks, Julie. So I just want to follow up on what Julie said, that the importance of these long-term observations, they're very valuable. Obviously, you know, the surfers are going and they're checking these things regularly, but we as scientists really need to have these types of observations to help bolster some of the other work that we're doing, which is on shorter time scales. This gives us a way to compare to things historically. So I'm going to show you some work on what are those impacts? How are these events, these things that we're measuring, specifically related to El Nino, how are they impacting the coastline? I'm going to allude to this here. El Nino is actually a really nice picture for us to think about future climate change. So we've got coastal impacts. The way that I think about it is sort of in terms of these two different boxes. So how do we think about changing oceanic conditions, and how is that going to impact coasts and their ecosystem services? And when I'm talking about changing ocean conditions, I'm talking about event-based things such as El Nino, but also things like climate change. So when sea level rises, how is that going to impact our coastline? How about changes in salinity and temperature? Julie showed you we've been measuring very high temperatures off of our coast as a result of this El Nino. And so we've got things impacting the coastline from the ocean end, but I'm really interested in also what happens from the upstream end. So what about freshwater flow? We think about, you know, how much rainfall we had this year. We've got precipitation, and our choices as humans in terms of what we use for water resources, how does that impact what's draining down the land to that coastal boundary? So we're thinking about impacts from both directions, okay, hitting that coastal boundary. And the really interesting thing about El Nino is that we can use it as sort of a window into the future, because El Nino, as I'll describe later, gives us conditions that are similar to conditions that we'll see in the future with predictions of climate change. So in particular, with El Nino, we're looking at high water levels. We have high sea level, as well as extreme conditions such as those high temperatures. And we have the potential for extreme precipitation events, although there's not a very strong link, as Julie mentioned, between El Nino and large precipitation events. In fact, hopefully you'll take away one thing from our presentation, is that El Nino has definitely been here very strongly this year. Despite the fact that we haven't had a lot of rainfall, we've had very significant showing of El Nino on our coastline. So I'm going to talk about impacts of El Nino, and I'm going to sort of work my way from the beaches. I'm going to repeat some of the stuff that Julie talked about on the beaches. I'm going to briefly talk about cliffs, and then I'm going to go further inland and talk about the estuaries. Here you have a picture of Torrey Pines State Park. That is the Los Penasquitos Lagoon, which is an estuary. It's essentially the connecting of those freshwater sources with the oceanic sources. And then I'm going to talk briefly about what comes out of estuaries, so the runoff going out into the ocean, we call those the plumes, and flooding that happens along the shoreline. So you guys have already seen this plot. This is a plot by Bob Guza and his team that they've been measuring beach width for many years. The time series actually goes further in the past. But what you see here is that the beaches, I like to call it breathe. They breathe on an annual basis. So they gain sand and get bigger during the summertime, and they lose sand and get smaller and narrower during the wintertime. This happens every year. This is a very natural cycle that happens as a result of the wave climate that's offshore. But you can see that there's a lot of variability within that. So we can see here in 2009-2010, that was a smaller El Nino, and we see that we had a lot of extreme erosion. And then we see this year, as Julie talked about, we started with extra wide beaches, which is, we think, a result of this nourishment where a bunch of sand was placed on the beaches. It was only placed on the blue, red, and pink beaches, but not on Torrey Pines, which is the black one. And that's actually a really important point here. So these three beaches started off a lot wider, and so they haven't gone as extreme as they did in 2009. However, you can see that Torrey Pines has really gone quite low and much lower than it did in 2009, 2010. And then this plot here shows you significant waves, so significant wave height, the maximum wave height that you're seeing, which is greater than 2 meters height, so about 6 feet. How many hours did that happen in a given month? And you can see that in our El Nino years, we're only partway through this winter season, we see more large waves. So this is a very big impact of El Nino that has drastic ramifications for our coastline, these large waves. It's not only the size of the wave direction also changes. So the waves are coming more from the due west in this case, down here in Southern California. So we have a clear link between the stronger waves that we see during El Nino and the erosion of the beaches to points that are more drastic than a typical year. This is a photograph of Torrey Pines State Beach. This is not at a high tide. This is actually at a low tide. And you can see how very little beach there is and how narrow it is, and there's no sand. The sand is all gone. It's all been swept offshore, and we now just have a cobble beach. There's also, when you erode this sand away, you expose structures that maybe haven't been exposed for a while. So this photograph on the right is from 1983. This is right in front of the Center for Coastal Studies at Scripps, so it's actually right down in front of the pier. And these rocks haven't actually been exposed to this extent since 1983, and we have them back again this year. You can go down and take a walk on the beach and check them out. So now we're going to move inland and we're going to look at the cliffs. You guys have probably heard of a couple major cliff collapses that have happened this year. We've had collapses at Sunset Cliffs, Torrey Pines, Del Mar. I'll talk a little bit more about some of those. This is just to show you that we've got other scientists, in this case Adam Young, working on cliff impacts from this El Nino season. So he's out there monitoring the cliffs with a variety of different techniques to do that, and he can actually start to measure the change in cliff height, but also the distance that it collapses. Some of you are probably familiar with this particular one. This is in Del Mar. Anyone who's been along Camino Del Mar, this the southbound lane is closed because of this massive cliff collapse that happened here. This one is actually a combination of effects. Not only do we have things happening on the ocean side, in this case we also had, this happened right after that major rainfall event that probably everybody remembers in January. And there was a big storm drain here. So you have a huge amount of water coming from essentially beneath the cliff. So you have two ways of affecting cliffs. You can have waves pounding the cliff, and then you can have runoff weakening the cliff from underneath. And then this is a picture of the collapse that happened in Sunset Cliffs recently. So we're seeing these impacts very strongly on the coastline this year, despite the fact that we haven't had, the large amounts of rain that a lot of people think we are supposed to. So now I'm going to get into, we're going further inland, and we're going to talk about estuary impacts. So this is my area of research. And I'm going to be showing you some results from Los Penasquitos Lagoon, which is the lagoon just north of here. This is a photograph this is Torrey Pines State Park, and this is the Highway 1 bridge. We're actually looking from the northern parking lot of the park. And this is the lagoon entrance during a high tide. So we've got a pretty large tidal swing that we see here. This is high tide, and then this is low tide. Really interestingly, if you look quickly between this photograph and the next one I'm about to show, you can see that the channel actually moved significantly. I'm going to switch back and forth between those two. These photographs are only a day apart. So what's happening here is massive movements of sediment, just like we saw on the beaches, right? So on the beaches, we were losing all that sand. We also have massive movements of sediment that are happening inside of these estuaries. And this year, in fact, it's gotten to the point where this is at the mouth of the estuary looking northward. While the sand was disappearing offshore, we had a buildup of cobbles onshore. This is a handrail, okay? You can usually, that's where your hand goes. So this is a significant amount of cobbles that were built up. And what this did to the estuary mouth is it actually created this berm. It blocks the estuary from being connected to the ocean. If you go to Los Penasquitos Lagoon right now, it is still currently blocked. And it's going to look like a big lake, a very big lake, because it's filling up, which I'll talk about in a second. And so what I'm looking at is how are these things connected? How is the effects on the beach connected to what's going on inside of the estuary? And then further, what does that mean for the health of the estuary? Estuaries are really important for both ecosystem resources, so there's a bunch of endangered species that live in them, including various plants and birds. There are also places that can become quite dangerous because they can harbor things like mosquitoes, which I'll talk about. And so we want to make sure that we are understanding how our estuaries function. And they also wind up being very important for humans. The ones in Southern California tend to be fairly small, so they're largely important to us from the perspective of recreational use. But we have other places that I consider estuaries like San Diego Bay, which are important for a whole variety of uses, including shipping, military, a very long list of human uses. So we want to understand how these things function, and we want to understand how they're responding to things like El Nino. So here we have this estuary that got shut off this year. And I'm going to show you a plot that I'm going to spend some time going through for folks that aren't used to seeing plots like this. This data is actually from December of 2014, and I can promise you that the data we have collecting right now is probably going to look similar, but the instruments are still in the water, so I can't show it to you. So this is from December 2014. This top plot is, the vertical axis is how deep you are beneath the water surface. The water surface is the dark blue line. Again, we're in Los Penasquitos Lagoon, which is just north of us. The color, so the red is velocity or flow going into the lagoon, And the blue is velocity or flow going out of the lagoon. So what we see here is as the tide rises, water level goes up, water goes into the lagoon. As the tide falls, it goes out of the lagoon. This is not at all surprising. We didn't need to take measurements to show this. This is just the tide flushing in and out of the lagoon on a regular basis. Down here, we have the dissolved oxygen concentration, so how much oxygen is actually in the water. And it actually varies on a tidal cycle, but typically it's staying relatively high at concentrations that are very safe for organisms that are living in the water. On December 11th of 2014, we had a very similar closure to the one that we have right now, although in that case it was sand that built up, not cobbles. So when the estuary closes, you can see that you lose that tidal flushing, which makes sense. It's no longer connected to the ocean, so it's not flushing any longer. What this does is it stagnates the circulation. And because we still have fresh water coming in from upstream, we wind up with stratification of the system. And what that is layering of the different types of water. So we have fresh water sitting on top of salty ocean water that was there from before, and it's very hard to mix those two water masses. So you get this very strong layering effect, this strong stratification. And what happens when you have that and no flushing is you wind up with a process called eutrophication, where we get growth in the upper layers of algae, phytoplankton. When that dies, it sinks to the bottom and it gets consumed by microorganisms and other organisms that are living near the bottom, and they're like us. They use oxygen to do their processes, and so they're using up the oxygen as they consume these dead algae. And as they use up the oxygen concentrations plummet, and we lose oxygen in the water column. This is a condition we call hypoxia. When you go beneath these concentrations, it's actually now dangerous for any organisms that need oxygen in the water. And in fact, this particular event, we saw floating dead snails and fish and lots of things that were dead in there. Now, this brings up a really interesting question about management of our coastal ecosystems. I'm going to just go back to this slide. A few days after this, the state parks, as well as the Los Penasquitos Lagoon Foundation, made the decision to do an emergency breach of the lagoon. The breach was done in part because of the hypoxic conditions, also in part because they were finding larvae of mosquitoes. Because not only did it shut off, but we had fresh water coming into the lagoon. That fresh water then gets trapped, and you harbor conditions that are good for mosquitoes, and so they needed to breach the lagoon. But unfortunately, they breached it mechanically, so they bring out bulldozers and they breached it, and they spent, in this case, it was about $8,000 that they spent on this to do a small breach, and it literally closed less than 24 hours later. So, how we manage these systems and what's the timing of which we do this is a big question. There's also a question of should we be managing it? Some people argue that we shouldn't. It's a very tricky question. We're in a place with these estuarine environments, particularly in Southern California, where we've impacted them so heavily that they're nowhere near their natural state. We don't even really know what their natural state is. So we do know from some historical records that these estuaries used to close naturally, but they also had the ability to open naturally in ways that we've now constricted, literally constricted. So with the bridges we've built, the estuary mouth is fixed. The estuary mouths used to actually wander around, and so as they wandered around, they could adjust themselves. We've also changed the freshwater inflow from upstream with dams as well as other alterations that we've made. And so that when you have a large rainfall event, it used to be able to flush out the system on its own, and now we can't do that. And so this raises a big question of management. And I think it's a really coupled system with managing the beaches. Julie and myself both mentioned this nourishment. that happened on some of the beaches. And this is something that, coastal managers are thinking about a lot because it costs a lot of money. I mentioned this most recent breach was only $8,000, but typically when they do a large breach, it's upwards of $150,000. So, and this is small compared to some of the other lagoons, which we're talking about almost $1 million. So it really, we start talking about large numbers quickly when we start thinking about how to manage these. So I'm going to move on now and talk briefly about coastal flooding and the plumes coming out of these systems. So these are some photographs that were taken on Christmas Eve where we had very large tides at Jolla Shores. And this is a photograph from San Dieguito Lagoon, the one just north of Los Penasquitos. This is the one where the racetrack is. And this is, again, a large tide event. And you can see that we're starting to get to a point where when we have an El Nino, we have extra water level, we add on tides, we add on waves, and we start actually flooding some of our coastal infrastructure. This is another photograph from Del Mar, January 23rd. And then this is that photo that Julie had from the video. And there's folks at Scripps that are actually working on how do we model this? How do we predict in advance what parts of the coastline are going to become flooded? This is a comparison of two different types of model from Timu Gillen, who is a postdoc at Scripps. On this side, this is a bathtub model where all you do is say, what's the ground level? What's the water elevation? Anything beneath the water elevation must be flooded. The one on the right, you can see there's a lot less predicted flooding. This one happens to be in Newport Beach. There's a lot less predicted flooding, and that's because this model actually takes into account the detailed physics of how water actually moves, and it also is taking into account the man-made structures that we've put in. And so getting really good, accurate models of coastal flooding is actually a really important factor for thinking about these impacts on our coastline, particularly when we think about what might happen in the future. We've also had this year, in addition to flooding and cliff failure and, estuaries having problems, we've had a lot of infrastructure damage. This is at Torrey Pines, where the parking lot that's along Highway 1 has been crumbling. This is part of an access way that fell off because of the large waves. So we're starting to see some of these infrastructure damages from these large wave events. And then the last piece is the Shoreline Health. This is a photograph from the day after that large January rainstorm event, and you can see these large plumes. These plumes, what make them visible is actually sediment in the water, but there's other things that come out of our storm drains besides just sediment. There's a lot of contaminants and pollutants, and we're trying to understand how those are impacting our coastline. This is a photograph, a very similar one where you're seeing sediment. This is at the border with Mexico, so this is the Tijuana River estuary. This one is particularly bad in terms of the stuff that's coming out of it. We have raw sewage as well as raw industrial waste that comes out during large rainfall events. And so we've been doing some recent studies to try to understand how does this stuff get on the coastline? Once it's there, how does it spread? We want to be able to better predict beach closures. Right now, 2 days after a rainfall event, we say, that's it, beaches are closed pretty much everywhere. Can we do better? Can we get a shorter time scale, a better accurate prediction on where and when to close beaches? Okay, so I've gone through a bunch of examples, and I want to now bring it home, and I've alluded to this several times, but I want to show you how all these different impacts that I've talked about are really giving us a window into what future conditions might look like. So future predictions under climate change scenarios are that we're going to have rising seas. Rising seas means we have more extreme water level events, because we have a background, and then we get this extra on top of it. Warmer oceans and air, larger but potentially less frequent. This is something that is a little bit more unclear. Storms, bringing big waves and potential flooding, ocean acidification, and reduced snow and ice cover. These are sort of the big picture things of climate change. Which one of these do we see during El Nino? So particularly on the US Pacific coast. So we do see enhanced sea level. El Nino itself actually leads to a bump up in the sea level because of the warmer waters as well as because of the atmospheric conditions. We have much warmer oceans and air, as Julie showed you the ocean temperatures. We don't necessarily get larger storms, although the ones we've seen this year have been particularly large, but we definitely always see large waves, and you've seen that. All of these impacts I've showed you have shown you the importance of the waves. And so really, El Nino sort of winds up being a little bit of a window into the future of what we might expect under a changing climate. This is a picture of sea level rise in particular, just because I want to show this particular effect. Everything over here is all observations. And as we move forward past the observations, we're looking at projections from a whole variety of climate models. And the blue curve versus the red curve with their error bars are whether we cut carbon emissions significantly or whether we continue with business as usual. So we're looking at pretty significant future sea level. But as I've mentioned, what we're interested in is the exact sea level at a particular point in time on the coast. So, if you go down to the ocean tomorrow morning, what is that sea level that you see at that moment you're out there caused by? So it's caused by a variety of things. You have these long-term risk factors like that sea level rise, but you also have things that sort of occur on a decadal cycle, such as El Nino and the Pacific Decadal Oscillation. So these are natural cycles that occur that can change sea level on top of that long term. And then we add on top of that high tides. So extreme high tides here can add about 7 feet, sometimes a little bit more, to the total water level you're seeing at the coastline. And then we add on top of that extreme storm wave setup and run up. And so it's all of these things added together that lead to the exact water level that you happen to see on the coastline. And some people see this and they think, oh, well then maybe sea level rise doesn't matter because it's small relative to how large some of these other natural variabilities can be. However, the important thing is that even if you have a small change in sea level, that means that the frequency of large events actually increases. So as we move forward in time, this is the number of hours of large events that are above historical levels. And so we get many, many more large events, sort of like what we've seen this year. So we have a background sea level rise because of El Nino, and then we're getting these large storm events, and they're having a very large impact on our coastline. And just to try to put it in a little bit of a quantitative perspective, background sea level this winter has been it ranges from about 8 inches, sometimes up to 15 inches higher than average. And that's sort of what we might expect to see 45 to 60 years from now based on these types of predictions. So this is what we're saying about it being this window into the future. So you can sort of think about these impacts you're seeing, and when you're out there on the beach, think about, what does our beach look like in 20 years? What does it look like in 50 years? And what is the best way to manage it? So in summary, Julie talked about El Nino. It's here. What are we measuring? She talked about measuring water temperature, waves, and flooding. And then we've talked about measuring the coastal impacts. So the impacts on beaches, cliffs, estuaries, flooding, and then shoreline health as well. And then I've sort of shown you that this is really a window into the future under climate change scenarios. And I don't really want to end on that depressing note. So what can you do? We have a couple citizen science programs going on right now where we have citizen scientists collecting photographs along the shoreline, and then scientists are actually using those photographs to help improve these coastal flooding models and to give us a sense of what damage has been done and where is it happening, where is it the worst. So what you can do is take photographs. The two different initiatives, there's an Urban Tides initiative, and in this case, there's a computer program and an app for those of you that are app savvy. And then for folks who may not want to use an app or would rather do it a different way, there's SCOOS that Julie talked about has a program called Storm Photo, and the websites for both of those are down here. And so this is a way that you can actually be involved in collecting some of the data to help us understand these processes better. So with that, I want to thank you, and I think we'll both take questions. The question was where are the cobbles coming from? And in most cases here, there's actually a layer of cobbles that sit beneath the sand year-round. Although a year like this year, we've actually seen the cobbles themselves moving around, and so there's a little bit of debate over whether there's potentially another source. But in general, we think of them as a layer that's beneath the sand. So this is literally the million-dollar question, or the multi-million-dollar question. How long do these nourishments last? And it really is what we're trying to figure out. Guza's been studying this for a while, and he does not put a number on it. He's hesitant to put an exact number on it. But clearly we see that they are lasting, but there's complications to that because we've seen some years where they last multiple years in a row and some years where they seem to disappear more quickly. And so they're trying to get into the physics of, okay, what years are they lasting longer and why, so that we can better understand maybe when and where would be the best places to place them.
So I think the question is there a similar case where we have programs on the East Coast and the Northeast in Maine that are making observations? And so I'm actually executive director of SCOOS, which is Southern California Ocean Observing System, but the U.S. is divided into 11 regions. And so now this is just one component, but I happen to know about it. In the Northeast in Maine, there's Narracus, the Northeast Ocean Observing System, and they are doing very similar measurements to what we have. They even have some of the coastal models, the shoreline flooding models that we have. They have some of the offshore buoys. CEDIP actually has some buoys in the Northeast, but they have their own measurements there that they are doing also. So I think every region, they're trying to build up this suite of measurements because everyone realizes how critical this is going forward to really quantify what's happening to our coastline.